Okay guys, here we are in week 6, and I think that we're going to use the first day of week 6 to worth of videos to kind of wrap up the stuff from the last test material. As some of you noticed, there were a couple of problems that I mentioned on the practice exam that we didn't quite get to, and a couple of you said, hey, I even looked at that postage stamp problem that was in the book. I think it's chapter 2, and I had a little bit of problem with it. Now the thing about the postage stamp problem is that it is a combinations problem, so you may have gotten stuck on it. If we were in class, we would actually spend an entire class day probably just working on postage stamp. So we're going to do a good portion of it right here, and your participation grade from this week, from day 1, will probably come out as something we do with this or with the Koch's sequence, which we're going to talk about in a minute, with the Snowflake, which is also wrap-up material. So this video will probably mostly be wrap-up material from the last test. If you noticed, I did not hold any of this material against you on test number 1, but it could always come back to smile at you on the final exam. So make sure that you understand all this stuff. So just real quickly, in your book, there are postage stamp problems, and it says something like this. The post office has only 5-cent and 7-cent stamps. And by the way, there can be lots of different denominations here. And by denominations, I mean like how many cents worth of stamps do I have. So this particular problem we're going to do is the 5-cent and the 7-cent stamps. I can't remember if that's the exact problem out of your book or not. I'll look in a minute. So by combining different numbers of 5-cent and 7-cent stamps, customers can usually get the amount of postage that they need. For example, 1 5-cent and 2 7-cent stamps, so 1 5-cent and 2 7-cent stamps. Well, 2 7-cents would be 14, right? And 5, so this will give them 19 cents worth of postage. Okay. So looking at that, they want you to talk about how many different combinations and what all's going on here. So 2 5-cent stamps makes up 10 cents in postage, and so on and so forth. So what it says is, number 1, show how you can make each of the following postage amounts by combining 5-cent and 7-cent stamps. And it tells you all of these are possible. So we're not trying to fool you or do anything weird. So I want you to think about these as I write them up here. 1 is 30 cents. 1 is 42 cents. 1 is 24 cents. And 1 is 51 cents. So think about some different combinations that may be able to help you to make these different combinations worth of postage if all you have is a 5-cent and a 7-cent. And while you're doing that, while you're thinking about it, excuse me, I'm looking in the book to see if this is the exact problem or if it's different in the book. Okay, so what do we think? 30 cents. If I wanted to make 30 cents, I don't even need the 7-cent stamp, right? I can just do 5-cent stamps. So what could I do there? 6 5-cent stamps, right? So over here I'm going to say equals 6 of the 5-cent stamps. Okay. What about 42? Very similar, right? Except for I don't need the 5-cent stamps. I only need the 7-cent stamps for that one. Okay, so if I did that, I needed 6 of the 7-cent stamps. That would make 42 cents worth of postage, right? Okay, so we're good so far. All right, then I have the 24 cents. So this is where it gets a little bit tricky. You're going to have to think about different combinations and things like that. So I know that 2 7-cents would be a 14. So in Webster Brain, what I do is I kind of look at what's going on in the back end here, and I know I need a 4. So I think, oh, 2 7s is a 14. So is there some way I can combine 14 with some kind of 5-cent stamps and get up with 24. Yeah, I could do what? 2 of the 5 cents. That would be 10 cents, right? Plus 2 of the 7 cents. That would be 14 cents. So 10 cents plus 14 cents. Oh, that's 24. We're good. So 51, maybe that looks a little bit daunting. I think to myself, wait a minute, I have a 1 at the back. Now I know with my 5-cent stamps, by the way, when we talked about divisibility rules a while back, we looked at the hundreds board and all that. I know that 5s can only go into things that end with 5s and 0s, right? So the 5 cent is never going to go into a 1 at the end. So I need to, that's why whenever I look at the 4 and I look at the 1, I'm thinking, hey, I need some combination that with the 7s that'll give me a 1 at the back end, right? So if I think to myself, 3 times 7 gives me 21, or what do I know that'll give me a 1 at the back? Well, I know 3 times 7. So I think 3 of the 7 cents, that's 21 cents, right? 21 cents. But what can I do with the 5s to make that come up to 51? Well, I've got 21 if I do this with my 7s. Oh, wait a minute, we already know 30 more. I can do that with 6 of the 5-cent stamps, right? Because that's 30 cents. Okay, so we see some different things coming in here. These are all groups of 5s. These are all groups of 7s. But now I've got different combinations of the 5s and the 7s going on. So I can tell, oh, wait, I'm going to have to do something where sometimes it might be okay if there weren't any 7s. Sometimes it might be okay if there weren't any 5s. But sometimes I'm going to need some combination of the two. This actually would, if we were doing this algebraically, we might start thinking about, hey, hang on a second, like just go ahead to your adult mind, not thinking about kids. Hey, I don't know how many 5-cent stamps there are. What if I let X be the number of 5-cent stamps? Right? Oh, we know X, it's a variable, no problem. Can I use the same variable for the 5-cent stamps that I used for the 7-cent stamps? Well, no, because here I had 6 of these and here I had 3 of those, right? Here I had 6 of the 7-cent stamps, but I had 0 5-cent stamps. So they need to be independent variables, not tied to each other, except for that they need to together make the combination that I'm after, right? So if X is the 5-cent stamps, then yeah, maybe I might let Y be the number of 7-cent stamps. Okay, and then I'm going to be pretty good because as long as I just count these 5 and 7, I probably can come up with some kind of an algebraic equation here that has 2 variables in it. Now, we haven't seen one with 2 variables, right? But I think, okay, I don't know how many x's, but every time I multiplied it by the value, right? So we did something like this, the value times the number, right, of the 5-cent stamps. And then we did the same thing, plus the value times the number. These were both of the 5s, these are both of the 7s. So how in the world can I write that as an actual equation? Well, it's probably going to look something like this. 5 x's, right? If you tell me there are 6 stamps that are 5-cent stamps, then I'll say 5 times 6, that's 30 cents, right? And I can give you the change amount that would be, the dollar amount that would be in pennies. Okay, and then what would this be? 7. We said Y was the number of 7-cent stamps. The value is 7. The number is Y. So probably we're looking at something along those lines. Okay. So this becomes an equation in 2 variables instead of just the linear equations and quadratics that we've been working with that only had 1 variable. Okay. Looking in your book, I see that on page 24, you should have already read chapter 2. The post office has stamps of the denominations 5 cents and 7 cents. It wants to know what amounts of postage you can buy and explain your conclusion, and then it says, what if the denominations were 3 and 5? What if it was 15 and 18? So they want me to come up with some other combinations, and that's fine. But I want to know this basic question, what sets that can I make? What combinations can I make? But really it's kind of even more important to say what combinations are impossible to make. Okay, so that's where I'm headed next. What amounts of postage are impossible? Really important, impossible for me to make if I'm using only 5-cent and 7-cent stamps. Okay, so it's kind of an interesting question because we will see as we kind of look into the number theory here a little bit that some weird stuff will happen to us later as we go on. So far, though, we don't know much in how to work with these things. We know there's different representations, algebraically speaking, that I can use for this, though. So I'd like to do a table because we've been doing tables, and I feel pretty comfortable with a table. So I'm just going to start out with postage amounts over here. And we're going to work through, and we're going to see, hey, which postage amounts, and we're doing 5-cent and 7-cent only. Okay, which postage amounts can I make? Which postage amounts can't I make? And how in the world do you know? And past a certain point, how do we know, hey, that one's going to work out okay, and everything beyond that works, and everything below that doesn't? So let's just start out. 1 cent. Can I make a 1 cent, a letter with 1 cent's worth of postage on it? No. Right? Because it's too small. The smallest possible I can make is 5 cents. Does everybody agree with that? Okay, so 1 cent is a no. 2 cents is a no. 3 cents is a no. And 4 cents is a no. Okay, right off the bat, I cannot make the first 4 postage amounts, period. Okay, but then I start thinking, hey, what about 5 cents? Of course we know we can make 5 cents. So I'm going to put it over here in my can do pile. Okay, so we can make, remember I'm looking for what's impossible. So I don't want to put the 5 cents here. Although you could if you wanted to. And I'm going to kind of group my stuff a little bit. We'll see how this goes for us. 5 cents I can make. What about 6 cents? Can I make 6 cents? No, it's still too small, right? It's actually halfway in between the 5 and the 7, so I can't make it with any weird combination. So that's not going to work for me. But of course I can make the 7 cents, right? So I'm going to stick him in his own little line here. So the 5's here, the 7's here. Okay, so what about 8? Can I make 8? No, again, it's the smallest next combination I can probably make is 2 5's, right? Because they're the small guys. So I can't make 8 cents. So I'm just going to say, hey, he's too small. 9 cents? No. Can't make 9 cents. But I can make 10 cents, and in fact, he's 2 5's, right? We know that one for a fact. Okay. What about 11? No, it's just a little bit too big for this one, right? We can't make it. Not big enough to pull in a 7 yet. So 11 cents, you're out of luck, buddy. Sorry. But hold on. What about the next guy? 12 cents. On first look, you might be going, oh, 12 is 6 and 6, or 12 is, you know, whatever. But hang on. There is a combination, right? I can make 5 plus 7 gives me 12, right? So he's not going to go in my can't make pile. Okay, he's going in my can make pile. So he's over there. 5 plus 7. All right, great. What about 13? Well, no, because he's just a little bit above the 5 and the 12, or 5 plus 7 gives me 12. He's not far enough to be 2 sevens, which, by the way, is next, right? 14. Yep, he's 2 sevens. So he's not far enough to give me that, and he's too far to be just a 5 plus a 7, right? He's just a little too close to that 12. If you want to think about some of these, then pause the tape and think about them. That's fine. Don't take my word for it. Mess with it a little bit and see what happens. Okay, so 14 worked. 7 times 2 gives 2 sevens would give me 14, right? And I come back to my table and I want to write 15, but then I go, wait. 15 ends with a 5. So he'll go up here in this stack, right? 5, 10, 15. In fact, if you wanted to, you could kind of go ahead and write out these guys, because we know here in this line, I'm just putting all the multiples of 7, for instance. 7, 14, 21, 28, 35, and so on, right? It's these that are down here that are the combination that might get us stuck a little bit. But kind of cool, we got 2 in a row, 14 and 15. And you can see where I'm going to have 2 in a row here for 20 and 21 even, right? So that's kind of nice. So 13 didn't work. 14 and 15 do. What about 16? Well, I could make 2 sevens, which would be a 14. It's only 2 away from 16, right? So that won't work. I could make 3 5s, which is 15. It's only 1 away from 16. So that won't work. I might be able to back it up to like 2 5s is 10, and then add on to that a 7, but that's actually 17, right? So I think 16 is not going to work for me. Oh, I actually just did the 17 for us, right? 2 groups of 5 plus 1 group of 7s. That's 17. Everybody agree? Okay, 18. 18 is 3 6s. I'm looking at it. I see 2 5s plus the 7. That gets me really close. There's no other way. Let me think. 14 plus 5 would give me 19, so it's not quite close enough. It is going to work for the next number for me, but it's not going to work for 18. So I feel like 18 is a no-go. That's impossible. But I just did 19, right? I just summed that one up. So that was 2 sevens was 14 plus 1 5 gave me 19, right? Okay, so we know 20 works. We know 21 works because those are just multiples of 5 and 7. What about 22? 22. Let me think carefully here. I don't see a 22. Hang on. Oh, I found it. Okay. If I did 3, okay, so what I'm doing in my brain, by the way, is I'm looking at all the combinations here with the 2 5s and the 1 7, right? So I could go 1 5, 2 7s. I could go 2 5s, 2 7s. Well, that would be 10 plus 14. I already talked about that one earlier. That was 24, right? But I said, oh, wait, I could have done 3 5s. That would be 15. Plus 1 7, that would be 22. Okay? So I can get to the 22. So, yay. So I can do 20, 21. I can do 22. Looking at 23, I don't see an obvious connection. You might try for the other combination, like 1 5 plus 3 7s. That would be a 21 plus 5 would be 26, right? Okay, so I feel like I'm getting away from the 23. So, okay, 23 doesn't look like it's going to work. All right. Oops, sorry. I put him down here in the bottom of my pile. 23 doesn't look like he's going to work. But then I go, hey, wait a minute. I'm getting a lot of numbers here together now, right? I've got 24, I've got 25, I've got 26. I don't have 27, but look at this. If I have 17, what can I do to that guy to get to 27? Yeah, I can just add a 10, right? So that would be 4 5s plus 1, 7 gives me 27. And now I start seeing an interesting pattern that comes in. If I can just get a string of about 9 or 10 numbers in a row, then what do I know? Yeah, I know if I get so far, then I can always just add 5 or add 10 to get me to the next group. In fact, I really only need a string of 5 numbers, right? So let's see if we have that already. We did 19, 20, 21, 22. I had to break 23, right? So that didn't work for me. But now I'm at 24, 25, 26, 27, 28. Oh, that looks like 5 in a row, right? So I'm thinking to myself, hey, wait, I can do all the rest of them. So can I do 29? Yeah, because here's 19, right? I'm sorry, I wrote over it. But 19 was 14 plus 5, right? So if I do 3 5s, that's 15. And then if I do plus the 2 7s, that's 14. 15 plus 14, that's 29. Huh. We already proved that we could do 30 because that was just 6 groups of 5. So think for me, what about 31? Can we make 31? I'm making the conjecture that we can. We just need to figure out, can we? Yeah. Okay, so let's go back up here. 21 is just a multiple of 7, right? And if I add 10 to it, which is a multiple of 5, I'll get 31. So how would that look? It would be 2 5s, that's 10, plus the 3 7s, that was 21. That gives me 31, right? Yeah, we're good. Okay. What about 32? Yep, I've got the 22 here, right? Plus 10. So the last number that we had an issue with was 23. So I'm thinking, well, I couldn't make 23, so I can't just add 10 to some number like I've been doing. So what about 33? If we can do 33, I hope you'll agree with me. Maybe you're convinced that if I can do through 33, then I can do every number above that. So let's check it and see. Okay. I've got a little bit of an issue here because I couldn't do 23 earlier. Let's see. And I haven't planned this one out, so I'm thinking in my brain. I really am thinking in my brain. Is there some combination of these guys up here that'll give me 33 is what I'm thinking. So I think if I did 12 plus 21, that would give me 33. Okay, so what would that be? That would be one group of 5 plus 1, 2, 3. Was it 3? Yeah. No. I'm sorry. 3, 4, right? 4 groups of 7. Sorry about that. So that's 5 plus 28. Is 5 plus 28 equal to 33? Yep. We got it. Okay. So now, hopefully, we're convinced, right? We did 24 before, right here, so we could just add 10 to it. We did 25, so we could just add 10 to it. We did 26, so we could add 10 to it. 27, we can add 10 to it. 28, 29, and now we're back at 30. So now we've got our 30 plus 10. Sorry, now we're at 40. So we've gotten all the way up through there. So it looks like the only numbers that are impossible are these numbers here. I've got 1, 2, 3, 4, 6, 8, and 9, 11, 13, 16, 18, and 23. So there's kind of a magical little something. I'm going to call it the magic number. About 23. So what's special about 23? That every number beyond that can be made. And I'm not answering that question for you. So what I'd like for you to do is I'd like for you to read through your book. And then if the book doesn't help you, go do some Googling. Google it up. And see what the heck's going on with 23. Why is it so special? Why is it that every combination beyond 23 works? So what makes 23 the special number? See if you can find that out, because that's kind of an interesting thing that happens here. Okay? Alright, so you can see why we didn't do postage stamps maybe before the test. It's kind of an unusual topic. It's kind of different from the other stuff that we were doing. So that's why I started to do it, and then I postponed it until after the test. So sorry about that. It's okay though. Now we have completed chapter 2. So, or at least most of the stuff in chapter 2 that I want to cover. So with that said, what you need to do is start reading chapter 3, right? Of course you do. So when you start reading into chapter 3, we also, let me throw this out here, we also did not do the sums of consecutive numbers. I really like that one a lot, but we just didn't have time to do it. It's a very Gaussian concept. We talked about Gauss earlier in the semester, how to add consecutive numbers. So start thinking about that. Look it up as you go. But yeah, we kind of just ran out of time. So if you'll start reading through chapter 3, building on number sense and number theory, that would be excellent. And in fact, I probably should have already made you read that chapter 3, because what we're going to do next is a little bit about chapter 3. So you're going to see some of that coming in here. So go ahead and read that and make sure that you feel confident with it, because we're just going to kind of expect you to do it. Okay. So what's the next thing that we're going to do that I'm talking about? We're going to do Koch's Snowflake. This was the other thing that was indeed on our review test, and I didn't have time to do it. I'm sorry. So we just ran out of time, and again, it's a little bit of a different concept, so I didn't want to mess with it too much before the test. This concept leads us up to something that's called fractals, which is a really popular concept in advanced mathematics. But the concept of it, the beginning concept of it, is very simple. School-age kids can do it, and in fact, I've seen some pretty young kids, like 3rd grade, 4th grade, doing fractal type things for projects for Christmas and stuff like that. And the Koch Snowflake is one of those things. So if you're looking at it, the way it starts is you start with an equilateral triangle, and then you come into each side of that equilateral triangle and you split it into thirds, and you erase one of the sides. Make a triangle coming out from it. Come into this side. Split it into thirds, take the middle third, make a triangle of it, erase this line there. Same thing on the bottom, okay? So the idea is now you go to every side of this new polygon, okay, which now the new polygon, let's count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. He has 12 sides, and all I've done is split the triangle one time on each side, right? I'm adding a triangle, a smaller equilateral triangle onto it. So if I do that again, these 12 sides here, I'm going to take out the center third, and I'm going to add an equilateral triangle and then erase, right? So that turns into this piece right here. Okay, and then that other side, and then the other side. So now I've got 12 sides that each of them is getting this extra little angly thing. I went from 3 sides to 12 sides, right? Now how many sides? Yeah, it's going to be a lot, okay? So we'll actually put together in a second what's going on here. But you can see I'm adding a bunch of sides. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 5, 6, 7, 8, 9, 40, 1, 2, 3, 4, 5, 6, 7, 8. It looks like about 48 sides. And we've only done this breaking it up thing twice. My gosh, we started with 3, we went to 12, now we're at 48. It looks like a sequence to me. And think about it, next what will happen? Maybe there's something going on with this. So there's some stuff really cool stuff that comes out mathematically in this as we look at it. We're going to take a little bit of time and talk about it, but it says here, there are 2 questions. If you were to continue this process infinitely, what would be the perimeter of the snowflake? And how do you know? Justify your response. And what would be the area of the snowflake? And how do you know? Justify your response. So let's think about this. We had a pretty, if this unit was 1 unit on each, maybe it's 1 inch on each side of that triangle, we had a pretty set perimeter, right? Okay, 1, 2, 3. The perimeter was 3. Then what about the area? Where the area should be 1/2 the height times the base, right? So the base is a 3. We'd have to figure out that height there, and then take half of all of that and multiply it all together. But I can get a definite area there, right? Okay. So what happens as I split up these edges over and over and over again? And if I do that infinitely many times, that's the question. So I'm going to show you a little bit of something here. I'm going to let you think about it. And your participation for the day is going to be about Koch Snowflake. So here we go. We want to know, the first question was about the perimeter. So if we think of the original side length as unit 1, this was the first question. Think of the original side length as 1 unit. We don't know what it is. Maybe it's an inch, maybe it's whatever. Okay? Then what happens is each iteration, that's what they're called, each time I break up a side, the 3 sides, the side will be some measurement as long. So we want to know what the heck's going on there. So let me just draw. And you know I'm not an artist, so bear with me. Okay. So if this is 1 unit long right here, and I break it up into thirds, as close as I can get, then this is 1/3, and this is 1/3, and this is 1/3, right? Okay. And then we said we're going to draw an equilateral triangle added on the edge here, right? Okay. And then we erase that portion of the original side. So if it's an equilateral triangle, those of you in my geometry class better know the answer to this. If it's equilateral here, this little triangle means that this side and this side and this side are all the same measurement. What are those 2 pink sides? What measurement? Yeah, they're 1/3, right? Each, because they got to be the same measurement. So now how long is this length? It's not a 1 anymore, right? Because I come up a third, I go out a third, I go in a third, and then I go up a third. So now this length became 4/3, right? Okay. And what's going to happen over here if we split it into thirds and add our equilateral triangle? Yep. 1/3, 1/3, 1/3, 1/3. And the same thing down here on the bottom. Of course, my lovely triangles don't look anywhere as near as good as the lovely triangles that were in that original picture, but you get the idea. So here we go. We're talking about what's going on with those links. So I can make a little table. Okay. I can say, okay, where did I start with? Well, I started at basically time equals 0, right? The iteration or the time. You could say which picture am I on or whatever. I'm going to make a 3-column guy here. Okay, so which picture and then what's the side length, and then what's the perimeter, because the question was what's the perimeter on this guy, as I do it infinitely many times, right? Alright, so at time t equals 0, or on the first picture before I start anything, nothing has happened. That's called your initial guy a lot of the times. That side length was a 1, and the perimeter was 1 times 3. Everybody agree? Because one side was 1, and then the perimeter, there were 3 of them, so I got a 3. Okay, what happened after the first division? I've divided 1 time each of the sides. So this guy right here, exactly the way I have him pictured. Get rid of these inside pieces, just the perimeter. Okay, 1 time. Each side length became 1, 2, 3, 4 thirds, right, is what we said. Okay, so the side length is 4 thirds, and there are 3 of them. That makes, those go away, 4 my perimeter. Oh, wait. You're telling me that when we split up each of those sides and we added, we actually made our perimeter bigger? Yeah, because the lengths are bigger, right? 4 thirds is bigger than 1 third, or bigger than 3 thirds, which was 1. So it's getting bigger. Oh, that's interesting. Let's keep going. What if I had done this twice? If I split this again, let's just do one side here. I would have an extra guy here, an extra guy here, extra guy there, and an extra guy there, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, what did I just do? 10, 11, 12, 13, 14, 15. Hang on a second. I think I miscounted. Sorry. Oh, I know what I did. Okay. So, I'm sorry. I totally just lost my train of thought. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of those pieces, right? Okay, and then I take them and I divide each of them up. It went from one piece, one big size piece, to 4 little size pieces, right? Okay, 1, 2, 3, 4, 1, 2, 3, 4. So I've split it up. Oh, I know what I was thinking. I'm sorry. Okay, now, whenever I look at this side right here, this side, I've got 1, 2, 3, 4, 5, 6. That would be what would happen in here in the original, but I took out the side, right? 7, 8, 9. So each of these little bitty pieces, even though I've got a lot of them, right? Each of these little bitty pieces is worth what? 1/9, right? Okay, of the original whole piece. So I can think, oh, I had a 1/3, 1/3, 1/3, and then I'm splitting each of those thirds into thirds. So that's 1/9, 1/9, 1/9, 1/9, 1/9, 1/9, and so on and so forth. So each of those little pieces is worth 1/9 of the original one, right? Okay, and then I got to think to myself, but wait a minute, how much is there? How much is there? 1, 2, 3, 4, right? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So there's 4 of them that are on each of those. So I've got a weird way that I wrote it earlier. I'm sorry. So I want to make sure I make this makes sense. So what I would want to do is I'd want to multiply that guy by how many times I see that piece, right? 1, 2, 3, 4, 1, 2, 3, 4. That's 8. 1, 2, 3, 4. That's 12, 1, 2, 3, 4, that's 16. And then I'd say, well, there's 16 on each side. Does that make sense? So there's 3 sides. So 16 times 3, what's that? Times 16 on each side. So 16 times 3 times the 1/9. It gets a little bit confusing, a little bit fast. Sorry, I just lost count of my sides. So I'm up here and I say, hang on a second. I don't think that'll reduce for me the way it is, but I think maybe I can do something with that. I can do the 3 and the 1, right? It won't reduce completely is what I'm saying. I can do the 3 and the 1, and I can reduce that down. 3 goes into 9 3 times. 3 goes into 3 1 time. Sorry about that. So what I've got is I've got 16 pieces that are all 1/3 long. So I'm going to call that 16 over 3, or that would be 5 1/3. So do we see what that looks like? Okay, so I'd like to kind of make it look a lot like what I had before so that I can make it see a pattern that's coming in here. So let me just go ahead and give you some numbers. The next one, you can follow this down if I did it a 3rd iteration, and I'm not going to draw that because it's just ugly as it is, much less if I do it again. I would take each of these thirds of thirds and split them into thirds again. So a third of a third of a third is 1/27. I hope that makes sense. Okay. So here I had 1/3 times 4 of those guys. Here I've got 1/9 times 16 of those guys. And here I've got 1/27, and I'd like you to take a guess at what you think that's going to be times. 4 times 4, right? 16 is 4 times 4. Does everybody agree? So I feel like this should be 4 times 4 times 4, which would be 64. Does everybody agree with that? 4 times 4 times 4. Do you see my pattern? See what's coming in there? 4 times 4 times 4. Okay, that's what's going on in each of those. So now whenever I see that pattern coming in, this is a 64 times, there are 3 of them, right? Because there's 3 sides. And times a 1/27. Well, hang on a second. I can still reduce that out, and that'll go with a 9. That'll be 64 over 9. Or if I reduce that out, 9 goes into 64 7 times. That would be 62, right? Oh, I'm sorry, 63. Let me get my multiplication tables in. And I'd have a 1/9 left over, 63. Okay, so I feel like I see a bit of a pattern. If you did it again, you'd have 1 over 81, and you'd multiply by 4 again. So something weird's coming in here. I think that if I had in the nth iteration, that this would be 1 over 3 to the n. Let's see about that. 1 over 3 to the 0 is just 1. 1 over 3 to the first is 1/3. 1 over 3 squared. 1 over 3 to the third. Yep, that's what's going on. And then here I'm multiplying by what? Here it was 4 to the first. Here it was 4 to the second. That matches up with the iteration I'm on, right? 4 to the third. What was going on up here? 4 to the 0 would just be a 1, right? So that would still work for me. So I think this is 4 to the n. Is that okay? Okay. And then what am I doing with it? Then I'm multiplying the whole stinking thing times a 3 because I did it 3 times, right? Okay. So 1 over 3 to the n times 4 to the n times a 3. Or if you were really thinking about it and you wanted to, you could stop right there because we've got a really good formula going on here. But if I was really thinking about this, this is 3 to the 1 on the top. This is 3 to the n on the bottom. There's an old exponent rule out there somewhere that says I can do 4 to the n on top. I can move this 3 to the bottom, but what exponent rule do I have to use? That's the negative exponent rule, right? So that would become 3 to the negative 1. And then whenever I tried to combine these, they have the same base, and they're multiplied together. So the 3 stays the same, and when they're multiplied together, what do you do with their bases? Like if it was over here in my scratch paper, x squared times x to the third, what we would do? Keep the base, add the exponents, right? Right? Example. Okay, so here I'm going to keep the base, add the exponents. What's n plus a negative 1? N minus 1. Right? We have a lovely formula coming in there. Now all I have to know about the perimeter is what the heck is going on with that, and how do I know? So this is actually a limiting idea, and we're going to get to limits a little bit later, and hopefully you've seen limits a little bit in maybe your 361, 362 classes, but the idea here becomes I'm going to look and see which one of these has the bigger exponent, the one on top, right? Because n is bigger than n minus 1, and whenever I put an infinity here, the bigger power on the top is going to win this tug-of-war thing that's going on. So this 4 to the n power will always be bigger than the 3 to the n minus 1, and the top is going to win that tug-of-war, which means as I go toward infinity, what's happening here? By the way, you should have seen something going on. 3, 4, 5 and a third, 7 and 1/9. The next one would have been 9 and 13/27. It's getting bigger, right? Is there going to be a stopping point if I go to infinity? No. So this whole entire thing, if I look at it as n goes to infinity, so does this perimeter goes to infinity. Okay, so it's kind of an interesting topic. The second question on the Koch snowflake said, what would be the area of the snowflake? So I'd like for you to kind of think about that one a little bit as well. It's also a neat little limiting idea. And what you're going to see, I'll just throw it up here so you can see it, so I don't have to develop it for you. In the area, if I add up the areas, each one's going to be 4/3 area. Area added is 1/3. You can see I've got this lovely little process going on here of what the area is that I'm adding. So this area that's being added, the exponent on the bottom, 2n minus 1, is bigger than n minus 1. So as we go to infinity, what's that mean? The bottom wins the tug-of-war. So the bottom's going to infinity, which means if I take that pie and I slice it up a million times, how big is your piece? Not very big. So this whole term is going to 0. So interesting stuff is happening there. I want you to take a look and think about it. Your participation question is going to be to tell me what the perimeter of the infinite iteration of the Koch snowflake would be, and hint, 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 we have an answer. So how big is your perimeter on that guy? It's hard to imagine sometimes, but that perimeter is going all the way to infinity. Alright, so I'm going to stop this and we'll come back for the day 2 notes. That wraps up everything that we had seen before the first test. This stuff was just little last minute stuff that was on your review we didn't quite get to. So hopefully you feel good about that. And, you know, never know when this will come back on the final exam or something. So hang on to your notes on this.